Review Day 9. Give it up for Day 9 of AP Review, where we look at electrostatics and DC circuits. So we start again with the fundamental charge in Coulomb's law. The most fundamental particles with charge are electrons and protons. Each carry a charge of magnitude E equals 1.602 times 10 to the negative 19th coulombs. You throw a negative sign in front of there if you're talking to an electron. So negative E is a charge for electron, okay? Unless you're a quantum physicist, and then it turns out that protons are made of even smaller charges called quarks. All right. As these particles are indivisible, again, false prophet photon, stop hiding your quarks. The charge of an object must be an integer multiple of E. So since we cannot break electrons and protons down any further, that means that the charge of every object must be a multiple of the integer multiple of E. Opposite charges attract, like charges repel. That's probably the most difficult concept you've encountered in AP Physics 1. I know, super difficult, right? And then again, yeah, this guy's a false prophet because in particle physics it turns out a proton is made up of quarks, but you don't need to know that for the exam. Charge interactions and polarizations. Electrically neutral objects still have charges due to electrons and protons present. It just means that their net charge is equal to 0. An electrically charged object will repel / attract electrons in a neutral object, causing charge separation in the object. The object is still neutral by charge conservation. It's just that we've moved the electrons so that they're more dense in one part of our object than they are in another. And we'll illustrate with these examples right here in a second. The principal question to ask: if I bring a charged object X close to a neutral object I, what will the charges within object Y want to do? So as an example, if I bring a negatively charged rod close to an electroscope, what will happen to the gold leafs? So if we do that, the gold leafs are going to separate. The reason being is that if we bring a negatively charged rod close to this electroscope, the electroscope has a net charge of 0, but there are still electrons and protons within it. The electrons are free to move, so they're going to be repelled away down into the gold leafs. So now you have a higher electron density up here and a higher electron density in this gold leaf. So we're going to have negative charges on the gold leafs, which means their gold leafs are going to repel each other since they both have negative charges. However, the net charge of the object will still be 0 due to charge conservation. This part right here will now be left with a positive charge. Same thing with the water bending that we saw in our first day of this unit, is that when we bring a positively charged rod close to water, the negative charges will be attracted, leaving a negative charge on this right side right here, while a positive charge is on the left side, and due to this attraction, the water is going to bend. However, the net force of the water is still 0, aka if you touch the water, you're not going to get shocked. And then again, here's just what we talked about a couple seconds ago. So the electrostatic force versus gravitational force, they look awfully dang familiar, to the point that we have this little meme right here. Right, so similarities, both are inverse square laws. The magnitude of the force drops off as the distance squared between the two objects increases, and both are conservative forces and obey Newton's third law. The differences: the gravitational force is always attractive, while the electrostatic is attractive or repulsive depending on the sign of the charges. The electrostatic force is much stronger, by a factor of approximately 4.17 times 10 to the 42nd for 2 electrons. You can notice this by the fact that if you put it this way, in terms of what we've seen, if you take a PVC pipe that's not charged and place it to water, there'll be a gravitational attraction between the water and PVC pipe, but not nearly enough to cause the water to bend. But you put some charge on PVC pipe and you bring it close to water, and now the water will bend. Hence, that's evidence that electrostatic force is much, much stronger than the gravitational force. Both have, again, that inverse relationship of dropping off as distance increases. Again, here's the graphs for it with gravitational force superimposed over electrostatic force. So the theory of resistors, aka return of la resistance. The resistance of a wire is determined by collisions between atoms and electrons, classically speaking, which depends on the following microscopic factors. The resistivity, which is a material property, the same way that with air resistance and friction, there was the drag coefficient and the coefficient of friction. There's a material property called the resistivity, which measures to what degree a material naturally allows electrons to flow through, or better said, allow would be conductivity, impedes the flow of electrons. So it's a material property, so it does not change for a material regardless of where you take that object or what you do to it. The length of the wire. The longer the wire, the more collisions will occur within the wire. Okay, so the resistance will increase. The cross-sectional area. If you increase the area, there's more space for electrons to move, so there's going to be less collisions. So if you increase the area, there will be less collisions, and thus the resistance of the material will drop. La résistance again. And then again, just an illustration here. We increase the length, there's going to be more collisions between electrons and atoms. We increase the area right here. That means that we're going to give more space for electrons to flow, and thus resistance will decrease. Series circuits, key features. The equivalent resistance is a sum of individual resistors. All you have to do is add the resistors in series, and that causes an increase in the equivalent resistance. Current is the same through all resistors, again by charge conservation. All of that charge is flowing from right here around to right here, has to be the same. So that means that current through R1 has to be the same as through R2, as the same through R3. Okay? Again, it's like the flow of a river, the current is the same throughout. The voltage drops for a resistor depends on individual resistance. More resistance, higher voltage drops. So if R2 had a higher resistance of R1 and R3, then the voltage drop across R2 would be the greatest. Again, you can think about that like a waterfall in terms of height. More resistance means that you're going to have like a higher height, higher kind of drop off. Kirchhoff's combine three words here. Kirchhoff's loop rule is the sum of states that the sum of voltage drops across R1, R2, and R3 must equal the voltage of the battery due to energy conservation. So whatever voltage you start with right here, when you're doing a circuit analysis, the voltage drop across R1, R2, and R3 must equal the voltage of the battery. Parallel circuits. Equivalent resistance is not the sum of individual resistors. Instead, you've got to be careful, okay? Adding resistors in parallel decreases equivalent resistance. Again, the idea being is that as you add more pathways, there's going to be more options for the current to choose from to flow through. Hence, resistance, the equivalent resistance will decrease. Okay. So again, we got to be careful of this equation right here. First, we're going to sum up the reciprocal of each individual resistor. So that'd be 1 over R1 plus 1 over R2 plus 1 over R3. Okay. So we get that number, and then we have to take the reciprocal of that number to get our equivalent resistance, okay? To determine how much current will flow through each individual resistor, again, you have to refer back to the idea is that the electrons have an option between R1, R2, and R3, so they're going to choose a path of least resistance. So if R1 has less resistance than R3, more current will flow through R1 than through R3. Kirchhoff's junction rule, it states that our current into a parallel component must equal current out. So I1, the current through R1, I2, the current through R2, and I3, the current through R3, if you add those together, must be equal to the current going in and the current going out. Again, the idea being is we think of this as a stream. There's no loss of water if you branch a stream off in a different section. So the same amount of water that goes into the branches must be the same amount of water that comes out. And a consequence of charge conservation. The voltage drop across each branch is the same. Again, the idea being is that if you break a stream off into 3 different branches, they're all going to undergo the same drop in height, assuming geographically it's a stable area. So the voltage drop across each section will be the same. Power dissipation circuits. If you're looking at the entire circuit, for a given voltage source, the power dissipation in the entire circuit depends on the current in the circuit. Okay? So that means we have to take a look at the equivalent resistance. The higher / lower the equivalent resistance in circuit, the less / more current, and hence power will be dissipated in the circuit. Okay? So that's what you have to think about. You have to think about current, and then concurrently, that depends on the equivalent resistance. So you have to think about the equivalent resistance of a circuit for the total power dissipated in the circuit. If you're looking at individual components, okay, for 2 resistors in series, the current through both is the same. So energy dissipated by each is determined by the voltage drop. Since the voltage drop is what's going to be different between the 2 resistors. Okay? So again, we look at the resistance of each individual resistor. The higher the resistance, the higher the voltage drop, so more power is dissipated. AKA if we have R1 and R2 in series and R1 is greater than R2, then that means that more power will be dissipated across R1 and R2, so P1 is going to be greater than P2. If you have two resistors in parallel, the voltage drop is the same across, so the energy dissipated is determined by the current. Okay? So resistance, so because voltage drop is the same, you have to focus on what is different between the two, which would be current. So we look at the resistance of each individual component to determine which one current is flowing more through. Okay? So if R1 is greater than R2, okay, then more current is going to flow through R2 than through R1, okay? Which means that more power will be dissipated across R2 since there's more current flowing across R2. So more power is dissipated across R2 than R1. So you have to be careful and distinguish between resistors in series and resistors in parallel because it can get quite confusing due to the fact that we focus on different factors for each type. Lastly, experimental techniques for circuits. To measure the current through a component, the ammeter needs to be in series with the component. The current through both the component and the ammeter will be the same due to charge conservation. To measure potential difference across a component, the voltmeter needs to be in parallel with the component due to the fact that the voltage drop across both is the same due to energy conservation. Okay, so ammeter in series because current is the same throughout. To measure current, voltmeter in parallel because parallel circuit components have the same voltage drop. Some test taking tips. This wraps up the course, but here are some test taking tips for you. Yes, this will look like you at the AP Physics exam. It's reality of it. So let's go over what the reality will be like besides Patrick's head being blown off. On test day, there will be conceptual questions. There will be mathematical questions. There will be questions that are both conceptual and mathematical. And there will be questions that you quite frankly just don't know the answer to, and that's absolutely fine. The idea behind the AP exam isn't meant to get 100%. We would love for that, but that's not the idea. The reality is there will be stuff that you just blank on, and that's perfectly acceptable. What happens on any test. You will come out of the test stressed, anxious, and second-guessing yourself. No, that does not mean you did poorly. No, that doesn't mean you're Patrick right here. That's natural to any high-stakes exam, especially one like AP Physics. Once you're done, here's my advice. Just let it go. There's nothing more you can do to change the exam. It's out of your hands. Relax. You survived AP Physics, but if you haven't had me for AP Calculus yet and you plan on taking Calculus, you'll still have me for AP Calculus. Dun, dun, dun. So test taking tips, more for multiple choice. Again, we have practiced this throughout the year. You have 1.8 minutes per question. I recommend 1 minute for conceptual questions and 2.6 minutes for mathematical questions. Roughly assuming that's roughly what it should be, assuming a 50-50 split of conceptual and mathematical questions. If pressed for time on mathematical questions, use the following techniques to whittle down choices. Think about what conceptually should happen to eliminate nonsensical answers, i.e. if I move further from a planet, my orbital speed will decrease, so options should be less than v, the original orbital speed. Take equations to extremes to see what happens, similar to above, i.e. this equation predicts if an angle of incline is 0, the acceleration will be g, which doesn't make sense for a flat plane. Use dimensional analysis to check if an option has the same units as what the problem asks for, i.e. this answer has units of meters cubed per second, but we're looking for acceleration which has units of meters per second squared, so it can't be correct. For response questions, use time recommendations for questions. They're assigned based on weighting of points. Show all problem-solving steps used to arrive to your result. Write down explicit equations with variables, not just numbers plugged in. These are often worth points. So if you have a question asking for force, and you have to use F equals ma to find it, don't just go F equals 2 times 3. Write down F equals ma, and then F equals 2 times 3. These are often worth points. Attempt every section, even if you blank. There's no penalty for incorrect answers, and a Hail Mary is a lot better than no response at all. And this covers the steps. Well, not the steps, and this covers the entirety of the AP Physics 1 review video series.